Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue talking about conditional independence. Quickly, we have just a couple of slides left. And then we will talk about base nets, which is the main topic today, inshallah. Last time we started to talk about conditional independence. We said that pure or absolute independence is rare in real life. Everything can be seen to somewhat interact with each other. But conditional independence is more realistic. And we said that two variables or two events can be conditionally independent on a third one, which means that if we know something about that third one, then knowing one of these two will not affect our belief in the other one. Okay, and we had multiple examples last time, and here is maybe a third or a fourth example. Let's say that we have a world where we model fire. So do we have fire or not? Is there a smoke or not? And if the fire alarm will go off or will sound or not. Okay, so we have these three variables. Now, do you see any of them to be independent? Is fire independent of smoke, or smoke independent of alarm, or alarm independent of fire? Do you see any of these three really independent? I don't think. The model in real life is that we have fire. The fire has smoke, and the smoke makes the alarm to sound because the alarm has maybe a smoke sensor. Okay, so these things interact together in some sense. But if we think about conditional independence, is there a way to think that two of them are conditionally independent given the other? So what do you think? Any ideas about that? So can we say any of these two are conditionally independent knowing the third one? If we know that the third one occurs or happened, then these other two are really become independent, of course, conditionally on the third. What do you think? Any ideas? We have fire, we have smoke, we have alarm. Noah?
Doctor, can we say that alarm and smoke?
Alarm and smoke are?
They are so like knowing smoke.
Yeah, knowing the smoke. So conditional on the smoke.
Yes.
The fire and the alarm are conditionally independent, right? Yes. If I know the smoke, then knowing that the alarm sound or not will not make any change in our belief that there is a fire, right?
Yes.
Okay, so fire and alarm are conditionally independent given smoke. Okay. Of course, in reality, fire and smoke are related, of course, right? And fire and alarm are related because if I hear the alarm, that means that there might be a smoke, and if there might be a smoke, there is a fire. That's the real scenario. But we can model it that way, given that we know that there is a smoke, then fire and alarm are conditionally independent. Okay. Any question about this? Thanks, Noah. Any questions? Okay, then let's see quickly that the relationship between conditional independence and chain rule. We know that chain rule holds anywhere and anytime between n random variables. If we want to compute the joint probability between n random variables, then we can use the chain rule. It is the probability of the first one times the probability of the second given the first times the probability of the third given the first two, and so on. So that's the chain rule. Okay. Now let's see what happens if we have conditional independence. First, without conditional independence, if we want to model the three variables that we saw last time, traffic, rain, and umbrella, we can say that this is equal to, using the chain rule, equal to the probability of rain times probability of traffic given rain times probability of umbrella given rain and traffic. Okay. Now, knowing if you remember from last time, that umbrella and traffic are conditionally independent given rain. Okay? That means that for this probability, you don't really need to include traffic. You don't need to include traffic because umbrella and traffic are independent given rain. So that means that this is equal to probability of umbrella given rain. So we don't need actually to model the chain rule exactly. Right? We need to have the probability of rain. That's in order to get the joint distribution. We need to model rain, the probability of rain, the probability distribution of rain. We need to also have the conditional distribution of traffic given rain, and we need to have the conditional probability of umbrella given rain, but we don't need actually traffic. So this will be equal to this, except that we will cancel out traffic here because we know that this one, in the case that umbrella and rain are conditionally independent given traffic, will be equal to umbrella given rain only. So that simplifies our model. Not only our model, the data that we include in our model. Now, given these three, we can get the joint distribution. We don't need to keep this big one. Of course, this is just a small example. If we have a bigger example, we have more variables. If we model many of them by conditional independence, then this will simplify the tables that we keep in order to get the joint distribution. Okay. What will help us doing that is BaseNet, or in other words, we call it graphical models. So you will see that BaseNet will allow us to model the distribution in a much simpler way than keeping the huge table or keeping even the tables that are indicated by the chain rule. Okay, that is because we will use and express conditional independence assumptions in these graphical models or BaseNets. So inshallah, from now we will focus on the BaseNet. Any question about this previous example, this slide, before we switch to BaseNets? Okay, so let me switch to BaseNets now. Okay, I think you see now the slides. Okay, now what is BaseNets? So of course, from the name, base. So we will use Bayes rule, of course, mainly in this model. And BaseNets means that we will see something like a network here. So what is the big picture of BaseNets? We saw that when we have the full joint distribution, we have a big problem that when we have so many variables, the joint distribution table will be huge. Okay? And as you know, the probabilistic model is a joint distribution. So we need to have a mechanism to compute joint probabilities whenever we need. If we need to keep the full joint distribution table, then we need, of course, a lot of memory, and it will take time to go through the entries in this table. And also, it will be really hard to learn such table in the first place. So BaseNets comes to the rescue here. It is a technique to describe complex joint distributions by simple conditional distributions. We call them local distributions because they actually represent local interactions between variables. So instead of saying that everything interacts with every other thing, we really focus on the basic interactions between pairs of variables, and from that we construct, or we can, if we will, construct the full joint distribution. Actually, we don't need to do that because we can compute any probability that we need from the small local conditional distributions. Okay? We call BaseNets graphical models, And as I said, they describe how the variables locally interact, and these local interactions, although they are really simple and they are in most cases they are between pairs of variables, but we can chain them together to give us the global picture, which is the full joint distribution if we want. Okay, so that's the main big picture of Bayes nets. We want to simplify the model. Instead of saying that everything interacts with everything, we just focus on local interactions. These local interactions will be expressed in conditional probabilities, in conditional probabilities tables. Okay? And for these simple, smaller, much smaller tables, we can compute any joint probability that we want. Here's an example for a car maintenance environment. So here we model some of the causes of problems in the car with the symptoms. So, for example, if I know that the car is not starting or won't start, maybe there is no oil, maybe there is no gas, maybe the starter is broken, maybe the alternator is broken, maybe the battery is dead. Okay, so there are some interactions here. For example, having a dead battery means that the battery is flat, and that will make the car not to start. Or it can be because of the problem in the alternator, and that caused no charging of the battery, which made it flat or dead, which will make the car not to start. Okay, so we model our problem with, of course, variables, and these variables interact locally. Okay, you see these arrows. We'll talk about this structure very soon in a couple of slides. But mainly, this is the idea that the interactions are expressed by these connections between variables, and they say that one variable interact or affect or sometimes cause the other variable. So if we have such network, if I have this symptom, I can say what is the probability that the fan belt is broken, or what is the probability that the alternator is broken, what is the probability that the battery is dead. So I can do such inference, okay, easily, as we will see. Now, what is the notation? What is the notation of the graphical model? Again, Bayes nets, sometimes they are called Bayesian networks. They are also called graphical models. All of these things are the same. In graphical models or in Bayes nets, we have nodes, okay, which is like weather here. They represent variables, of course. Okay? And these nodes can be observed or unobserved. Okay? When a node is observed, usually it is dark or shaded. Okay? If it's unobserved, then it is open or white. Okay? So the nodes are the variables. Now the arcs or the links between the nodes represent interactions. Okay? This is very similar to the constraints in the CSP session that we had. Okay? Here they represent relationships between the variables, okay? And indicate direct influence. So this is between an arc between two variables indicate direct influence or direct interaction between the variables. Okay? Formally, as we will see later today, they actually encode conditional probability, conditional independence, okay? As we will see, inshallah, later today. Here's an example. Cavity causes, and cavity also causes catch. Okay? So we have three variables here. We have cavity, we have toothache, and we have catch, and we have the connections that indicate the influence or the interaction between the variables. Okay? You might say, okay, toothache and catch are also related, right? Because if I have a toothache, I might have a cavity, and the cavity might lead to a catch. Yes, and that's encoded, but indirectly. Right? So the relation here is indirect, so it's not explicitly mentioned in the model. It is mentioned through the other links, as we will see. So we can actually compute using the Bayes net the probability that if I have a toothache, what is the probability that I have a catch, and vice versa. Okay, so there might be interaction, of course, but it's encoded indirectly. It's not encoded directly in the model. What is coded directly is the direct interaction. So we believe that cavity affects directly toothache, and we believe that cavity affects directly edge in this model. Okay, so for now, actually, we will just for simplicity, we will think of the arrows as direct causation. Okay? Just for now, but by the end of the lecture, you will see that it's not always the case. This connection doesn't mean always causality. Okay? But for simplicity, for now, just to get a good understanding, until you get a good understanding of Bayes nets, you can think of this as causations. So cavity causes toothache, that's why we have a link here, and cavity causes catch, that's why we have a link here. Okay? Here's an example. I want to model independent coin flips. How can I model them using Bayes nets? Well, all of them are independent, right? So there should be no interaction. There will be one node for each coin, for the outcome of each coin, but there will be no interaction. So there will be just separated n nodes. There's no interaction at all between them. So x1, x2, up to xn. So that will be Bayes nets for the world of flipping n independent coins. Of course, that is very simple. Okay? So no interactions between variables, which means absolute independence in this case. Another example: rain and traffic. Rain and traffic. Okay? So we have two variables. So we have two. We will have two nodes, okay, R and T. And since we believe that rain causes traffic, then we should have an arc from rain to traffic. Okay, so that's a Bayes net now that that presents traffic. Okay, so forget about this now, and let's see what are the models that we can have. The first model is complete independence. So we don't think in that model, we don't think that rain and traffic interact at all. So we can model them just by separate nodes. That's a model. It might not be good enough, okay, but this is a Bayes net model. But this model encodes complete or absolute independence between rain and traffic. Another model that we just drew, which encodes the relationship between rain and traffic, simply rain causes traffic. So there will be an arc here. Okay. Now, what is the difference, or what makes model 2 here better? Yes, it encodes reality. It is closer to reality that we believe that rain causes traffic, or rain influences traffic. But it's not only that. This allows us to really do inference. Like, we can now compute the probability that we have rain given that we have traffic, or the opposite, probability of traffic given rain. We can do that using this model, but we can't do that using this model at all, because they are independent. Okay? So in this model, probability of R given T is what? Is equal to probability of R, because they are independent. Right? So knowing T doesn't affect at all the belief in R. Okay? So that might not represent reality in the best way. But again, these are two models, possible models in some cases. But you need to understand, or the point from illustrating in this slide is to make you think about the differences in terms of the assumptions that we have, and also in terms of the inference that we can do on these graphical models. Okay, any questions so far?
Doctor, so in any example, I can have like multiple models, yeah, and I cannot say that it is wrong, but it is better. This is better than this.
Yeah, of course. We will get to that. We'll get to that. For this specific one?
Yes.
for rain and traffic, there is no other model than that. You can also say train goes to traffic goes to rain, but it's we'll see by the end of the lecture that we can do that also. So actually, the direction of the arrow here, although it's better to be intuitive, but it doesn't matter much. Okay, as you will see by the end of the lecture, inshallah. But we will also see examples that have more than 2 variables, and examples that sometimes we want to encode explicitly independence. Okay, we'll see that inshallah very soon. I think that maybe in the next couple of slides. Any other questions? Okay, let's go through the next example. Let's build the causal graphical model now. Iman, do you have a question? I didn't get that. Can you pick up the mic, please? Okay, so okay, let's continue then. So here we have some variables. Let's go through them. So the first one is traffic. Okay, so we'll have a node for traffic. Okay, that's a bit more complicated than the previous one. Then we have rain, and I think we agree that rain causes traffic. Okay, then we have low pressure. Low pressure. Okay, from physics, you know that low pressure will lead to it can lead to rain, right? Okay, so I can say that L causes rain. Okay. Have roof drips. Roof drips. So when can we see water coming down from the roof of the house or the roof of the building? Okay. Of course, when it rains, right? So we can have here D, and the rain causes the drop, right? Then there is a football game. There's a football game. So what do you think? Where should we add the football game? Is there any interaction between the football game and any of these? The football game will cause rain? I don't think. The football game causes dripping of the roof? I don't think. But it might cause traffic, right? So I made it hard for myself, but I will write it here. F can cause also traffic. Okay. Cavity. How about cavity? Does it interact with any of these? No, doesn't interact with any of these. I don't think it causes traffic, or it causes low pressure, or it causes dripping or anything. So we can just write it independent of anything without any interaction, like that. Okay. And that's it. Okay, so we don't have any more variables. So that's an example of thinking about the graphical model of a specific environment, okay, using the interaction between the variables. Of course, if you see here, low pressure will influence traffic and will influence the roof dripping, okay? But indirectly. Also, I can reason between football game and rain, and football game and low pressure, and so on. So we can get as we will see inshallah with probabilities, we can get we can infer the probability of any variable given the other, or we can infer the entire joint distribution. Okay, but the point so far in the lecture is how to model the interaction between variables. Any question about this? Everything is clear? Tama.
So, doctor, in this case, we can say that, for example, if I have two nodes that are not directly connected, in this case, F and D, so I can say that they are indirectly connected.
If F and D?
Yes.
Okay, so your question is whether F and D are, we can say that F and D are indirectly connected. I don't like to say it that way. I can say that there is some interaction between F and D, but it's not directly captured here. Okay? What is captured is the direct interaction, and this is what we actually need in the model. Okay? So there is indirect, of course, influence between F and D. Or we can reason there's some correlation. I would say it that way better, I think, because the football game doesn't actually cause the dripping of the roof, but there might be some correlation at some time. Okay, so I would like to say it that way, but the direct interaction is are encoded explicitly in the graphical model using the arcs. Did I answer your question, Emma?
Yes.
Okay, any other questions? Okay, so let's move on to another example, the alarm network. This is a classical example in Bayesian networks. So what are the variables here? The first one, burglary. A burglary happening in the house. Okay? Like a thief is trying to steal something from the home or not. Okay, so there's a burglary or not. That's the first variable. So we can just say B here. Okay. Then the alarm goes off with sound. So what is the relation between A and B? Okay. Usually, if there is a burglary, then the alarm will sound. Okay, so alarm will go off. So, so I think intuitively we can say B causes the alarm. Okay. Me. Okay, then Mary calls. Mary can call at any time, right? So Mary is a friend. So the event of Mary call can happen anytime, but in such environment, probably we can model that the alarm Mary heard the alarm in Mary is a neighbor of me of the age. Okay, so Mary heard the alarm, and thus she is calling. Sometimes she calls without, of course, hearing the alarm because she is my friend. But probably for this environment, it is caused by the alarm. So we can say that the alarm causes Mary to call. Okay. John also can call, and sometimes he calls me to just check on me, or sometimes he calls because he heard the alarm, right? So the alarm also can cause John to call me. Okay. Then there is an earthquake. Where can we model the earthquake here? Okay, so we can think that sometimes the alarm goes off or sounds if there is an earthquake. It will be a false alarm in this case, probably because the alarm here is for burglary, but it can happen, right? So we can think that the earthquake causes the alarm to go off, to sound, right? So that's the network for this environment. Any question about that? Questions? Okay, very good. So let's yeah, questions, Nama? Nama, your mic is on. Okay, so let's continue and let's see what are the semantics. So we saw the structure. We saw a couple of examples from the traffic and from the alarm network of the structure of the model. Now let's talk about semantics, the meanings. Okay? We said that we have a set of nodes, one for each variable. the Bayes net is actually a graph, and more specifically, it is acyclic graph. What do we mean by acyclic graph? We don't have cycles. And that's intuitive, right? Because we should not say that A causes B, and B causes C, and C causes A, right? So that's that's a cycle that is not in reality, right? And it's otherwise something will go forever. Okay? So it is intuitive not to have any cycles in the graph, especially if we think about causality. Then what is the meaning of each node, or what we will keep in each node? So far the model is just nodes and arcs, right? And we don't know where is the probability there. Okay, here comes the probability. Each node encodes or has a table called conditional probability table. This table represents the conditional probability of that variable given its parent variables. So here we have x. X has n parents, a1, a2, up to an. So the table that will be associated with this node is the conditional distribution of x given a1, a2, up to an. We call it conditional probability table, or CPT. So each node here has a CPT. CPT representing what? Representing the probability of that variable given the values of the terms. So that's a conditional distribution. Of course, there will be multiple conditional distribution for each possible combination of values of the parents. And that's it. That's Bayes net. So a Bayes net is a topology or structure, which is a graph. The graph is acyclic, which means that it doesn't have any cycles. It's directed, of course, as you saw, and you can think of the direction as causality for now, but it doesn't have any cycle. And plus the graph, or plus the topology, there are local CPTs. Why do we call them local? Because the conditional probability tables here represent the relation between the variable and its parent only. Okay? So if we have any interactions here, we don't care about what are these variables in this table. We care about them when we talk about the CPT of AN and when we talk about the CPT of A1. But the CPT of X, it represents only the probabilities of X given its parents. Okay, so that's why it's called local conditional probability tables. Now, where are and what do we get out of this? Yeah. So what do we get out of these probabilities? What do we get out of these probabilities? We said that each node encodes, and associated with each node, there is the conditional probability table. Okay? Actually, the collection of all of these conditional distributions encodes a joint distribution. So in Bayes net, the joint distribution P of x1, x2 up to xn is the multiplication of all the conditional probabilities from the nodes. So this is a multiplication from I1 to n. What is n? N is the number of nodes here. P of xi, each variable given its parents only. This is what is encoded implicitly by Bayes nets. This is, if you want to represent Bayes nets in one equation, then this is P1. The joint probability is equal to the multiplication of the conditional probabilities of the individual variables. The conditional probabilities are, of course, conditioned by only the parents. as we just mentioned, using the CPTs. Okay, so of course we will explain this, but this is the main idea. If I want to encode the relation, or if I want to see the joint distribution table, I can compute it just from the local CPTs, because this is what is encoded in the local CPTs, right? We said that each CPT, each conditional probability table, is the conditional probability of the variable given the parents. Now I'm saying that multiplying all of these probabilities will give us the joint probability. Okay? So that means that instead of having the huge giant joint distribution table, I can only have the local tables, which are the local CPTs only from the BaseNet, and from that I can calculate any joint distribution, joint probability that I want. Okay? So to see what probability a BaseNet gives to a full assignment, just multiply all the relevant conditionals together, like what we see here. Example, let's say that we have this probe cavity network, and I want to compute the probability that we have plus cavity, plus catch, and minus tooth thick. What will be that probability using BaseNet, using what we have here? This probability will be the multiplication of the conditional probabilities. Okay? So what are the conditional probabilities? Cavity doesn't depend on anything, right? So we will just have P of cavity, P of plus cavity here in this case. So P of plus cavity times P of, so let's go through every variable, right? So that's what this multiplication tells us. Go through every variable, and we get the conditional probability of the variable given the other variables, given the parents in this case. So this is probability of plus cavity, probability of toothache. We have minus toothache here. Let's go with the catch first, or the order. Doesn't matter the order, of course, but let's go with that order. Plus cavity, plus catch, given what? Given cavity, because that's the parent of catch. Given plus cavity times the probability of, what's the third one? We had cavity, we had catch, probability of minus toothache, given its parent, which is plus cavity. And that's it. That's the probability. That's how we compute that probability. If we have the conditional probability tables here, then we can compute this probability using these. Where is P plus cavity? It's here. Where is P plus catch given plus cavity? It's here, somewhere in one of these rows. Where is the probability of minus toothache given cavity? It is also in one of these rows. Okay, so we can compute it. If you look at this equation, this is not the chain rule, right? The chain rule says this will be probability of plus cavity times probability of plus catch given plus cavity times probability of minus toothache given plus cavity and plus catch, right? So that's the chain rule. But actually, what the BaseNet allows us to do is this: is to only think of the conditional probabilities only expressed between the node and its parents, not anything else. And the reason is that, I think you would guess it now, the reason is that this assumes conditional independence with any other variable. With any other variable. So having minus toothache here, sorry, having plus catch here, with this doesn't matter, because we assume conditional independence. If you didn't get that, that's fine. We will explain it later today or next time. But for now, this equation is different from the chain rule. okay, because of the way that we express the joint probability here by a multiplication of the conditional probabilities included in the CPTs or the conditional probability tables of the base net. Questions? Any question? Is everything clear? Okay, good. Okay, now, why are we guaranteed that this setting results in a proper joint distribution? Why actually multiplying all of these conditional probabilities will give us a joint distribution? Well, the chain rule is different, right? The chain rule says this joint probability is the multiplication of the probability of a variable given the previous ones. That's the chain rule. Okay, look at this part and compare it with this part. What's going on here? This one says x1 given x1 and x2 and x3 up to xi minus 1, all of the previous variables. That's the general chain rule. What happened here? We said that instead of having all of these variables, we'll just keep the parents of xi only. So that's the main difference. That means that any one of these variables that are not in the parent, that is not a parent of xi, we will exclude it, which actually encodes conditional independence. Didn't we say it last time that P of A given B and C, if it's equal to P of A given B, that means that A and C are conditionally independent given B. That's why we said that knowing C will not affect the belief in A, given that we know B. So we will just cancel C. That's only because A and C were conditionally independent. So that means that if we do it here, that means that any variable that is not a parent of xi is actually deemed conditionally independent with xi given its parents. Okay, and this is the main idea of base nets. The fact that it encodes this conditional independence explicitly. Okay, so we here assume that the we assume the conditional independence. Okay, so P of x1 up to xi equals to P of xi given parents only. Okay, so we only have here the parents of xi. And the consequence of that, because we assume this, then we can replace this probability by this probability, and we get the rule of the base net that we had in the previous slide. That the joint distribution, the joint probability, is equal to the multiplication of probability of xi given its parents only. Okay, that will make our life much easier because we only need to think of local interactions. If we have xi here, we look at its parents, and the conditional probability table will be xi only given its parents, not everything else in the network. If we have 1,000 variable, xi only has 2 or 3 parents, then this table will have just include the values of 4 variables instead of 1,000 variables. Okay. This is just a note that not every base network can represent every joint distribution. By this assumption, it's not the case that the base net can represent any joint distribution. Because it has assumptions, right? There is an assumption here. If these assumptions don't hold, then it cannot be represented by any base net. Every base net encodes encodes some conditional independence assumptions. Okay? And these conditional independence assumptions, of course, influence the joint distribution. Okay, that's the idea here. Now let's go through examples. Here's a quick quiz. We have n variables. Again, this n coin flips. Okay, so this is the network. The network has no interactions at all, which means that in each node, generally we have a conditional probability table, right? But because here every node is independent of the other, there's no parents. In other words, then we have just a probability distribution for each variable. That's the simplest case. So if I want to compute P of the joint distribution of all of these variables, head, tail, head, this will be just probability of head times probability of head from the first. So that's from the first. That's from the first coin. That's from the second, and that's from the third here, and that's from the fourth. Of course, if they are all the same, they have the same distribution, then it will be the same probability. Okay? But generally, if we have just n different coins, then maybe they have different probabilities, but we'll just plug them here. You see here, there's no conditional probabilities just because we assume complete independence. It's pure independence. Right? Still encoded in the base net. How? Because we didn't have any interaction, so there's no actually dependency at all. The CPT here will be reduced to a probability distribution without any conditions. That's the easiest form. Now let's go through a bit more complex network, which is the network of the rain and traffic. So rain causes traffic. Here we have two nodes. For the first one, there are no parents, so it will be a simple probability distribution. Here we have this node has one parent, so the probability, the CPT, the conditional probability table here, will encode the probability of T given R. So for every value of R, we will have a conditional distribution. So when R is plus R, we have this distribution. When R is minus R, we have this distribution. So this is what we call the CPT of P. Okay, now I want to compute P of plus R and minus T. How can I do it? Any ideas? How can I do it using BaseNet? The main rule says the joint distribution is equal to multiplication of the conditional probability. So the joint probability is equal to the multiplication of the conditional probabilities for each variable. Okay, so for each variable, what is the conditional probability and how we can get it? Any ideas? More?
Doctor, can we say first probability of plus R?
Yes, probability of plus R. Given anything?
No.
No, why not?
Oh, because the condition.
Because what?
Because we have first to multiply it then with the condition, or I'm doing wrong?
Because we don't have any parents here, right?
Yes.
There are no parents here, right? We don't have this. So there is no condition for R. So we'll just have probability of plus R. Right?
Yes.
Anything else?
Then we want to multiply it by minus R, probability of minus R.
Minus
T,
R or
sorry.
minus T? Minus T.
Minus T. Okay, then we will, but minus T, I think, will be with the conditional with the plus R.
Yes, of course. Minus T comes from T, right? That's a value of that variable. That variable has one parent, which is R, right? So we'll have to condition on the value of that variable. What is the value of R? It's plus R, right?
Yes.
So we'll have to have here minus T given
Then plus R.
Plus R. Very good. Okay? And you will directly have these values in the table, by the way. Directly. Where is probability of plus R?
1/4.
Yeah, this one. Right? So this is 1/4 times probability of minus T given plus R. Where is it?
1/4 from the first table down.
Yes, so that one. Right? This is given plus R, and this is minus T, so that's also 1/4 So that will be 1/60. Okay, I think we'll stop here, and inshallah we'll continue next time. But I hope that now the idea of a Bayes net is clear. It encodes conditional independence. We only have at first it's a graphical model. It has nodes and arcs, and arcs can generally express causality. We'll relax that a bit next time. At each node we have the CPT table. The CPT encodes or express the conditional probability of the variable given its parents only. Okay? And we said that this allows us to encode or actually mean conditional independence. Okay, and by that, any full assignment joint probability can be computed directly from these tables. Okay, so it will be the multiplication of the variable given the value of the variable given the value of the parents of that variable for every variable. Any questions? Okay, then inshallah talk to you on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.